We'll start in 1 minute. Today we'll be in section 7.7 on approximate integration. So we begin by letting f of x be a continuous function on the domain interval from a to b. And there are a few ways that the definite integral of f of x dx from a to b can be approximated. In all of these cases, we're going to subdivide the interval from a to b into n subintervals, each of length delta x equals b minus a over n. And we define the endpoints of the subintervals as follows. The left endpoint A is the same as x sub 0, and then x sub 1, x sub 2, and so on. At the other end, x sub n is the same endpoint as B. In Calculus 1, you learned how to approximate a definite integral using the left endpoint approximation. It's also referred to as the left-hand sum. Okay, so you might remember if you subdivide an interval from a to b into n subintervals of equal length, and suppose we have a graph that looks something like this. This is the graph of f of x. And if f of x is greater than or equal to 0, then this definite integral of f of x on the interval from a to b, the last endpoint x of n is the same as b. The value of that definite integral is just the area below the graph of f of x and above the graph of the x-axis on the interval from a to b. So using a left-hand sum, we construct we construct rectangles, and the height of the rectangle is determined by the left endpoint. So this ordered pair is x sub 0, f of x sub 0. On the interval from x1 to x2, we construct another rectangle, and using the left endpoint x1 determines the height of this rectangle. So this ordered pair is x1, f of x1. And so on. We keep doing this. This one is not to scale, but on the other end, we have x sub n minus 1 to x sub n. We construct a rectangle using the left endpoint to determine the height of that rectangle. So this ordered pair is x sub n minus 1 f of x sub n minus 1. The length of each subinterval is delta x. So to approximate this definite integral, we just add up the areas of those n rectangles. And so on. So the area of each of those rectangles is added up. So the integral from a to b of f of x dx, which is the left endpoint approximation, or the left-hand sum. Well, what's the first term in the left-hand sum, or the left endpoint approximation? The first term is the area of the first rectangle. The height of the rectangle is f of x sub 0, and the horizontal length of that side is delta x. Then the second rectangle, what's the area of that? Well, the height of this rectangle, the second one, is f of x sub 1, and the base length is delta x, and so on and so on and so on. At the other end, the final rectangle, the height is f of x sub n minus 1, and the base length is delta x. And then we can use the sigma notation for the left endpoint approximation. So sigma, this is the capital Greek letter that we use to represent the sum of a certain number of terms. So we're going to add n terms. We'll begin with I equals 0 and go up to n minus 1. And then the terms that we're adding have the form f of x sub I times delta x. So you probably remember that from Calc 1. So this is an example of a Riemann sum. In particular, this is the left endpoint approximation, or the left-hand sum. Okay, well, analogously, we have a right endpoint approximation. So maybe we can go through this one a little quicker. So this time we use right endpoints of subintervals to determine the height of the rectangles. So we have y equals f of x again. And on the interval from x sub 0 to x sub 1, we're using the right endpoint to determine the height of the rectangle. This is for the right endpoint approximation. So this ordered pair is x sub 1, f of x sub 1. And then on all of the other subintervals, we use the right endpoint to determine the height of the rectangles. So I'll label a couple more of these. This point is x sub 2, f of x sub 2. And we need the last one, so the last one is x sub n, f of x sub n. And then the right endpoint approximation of the definite integral is the sum of those rectangles whose heights are determined by the right endpoints of the subintervals. So we're finding the area, I'm shading in the area. All right, so the definite integral of f of x from a to b, this time the right endpoint approximation, or sub n. The first term, the area of the first rectangle, f of x sub 1 times delta x. The area of the second rectangle, f of x sub 2 times delta x. And so on. The area of the nth rectangle, f of x sub n times delta x. And then the sigma notation, this time we start with I equals 1 and we go to n. And the individual terms have the form f of x sub I times delta x. Okay, the next one is called the midpoint rule. So the midpoint rule. So on the intervals, we use the midpoints of the intervals to determine the heights of the rectangles. If we have the graph of some function y equals f of x, so this first midpoint on the interval from x sub 0 to x sub 1, the midpoint determines the height of the rectangle. We refer to the midpoint of that interval, so pretend like this is in the middle between x sub 0 and x sub 1. We refer to that as x sub 1 bar. I'll explain more explicitly what x sub 1 bar is in a minute. But the height of the rectangle is f of x sub 1 bar. This ordered pair, x sub 1 bar, f of x sub 1 bar. And then we do the same thing on the other intervals. Okay, let's label a couple of the other points. This point, x sub 2 bar, f of x sub 2 bar. And we need the last one, x sub n bar, f of x sub n bar. And the width of each of those is delta x. Okay, so x of I bar, if it's the midpoint between x of I minus 1 and x of I, then what's the formula for x of I bar? X of I bar is just the average of the endpoints, x of I minus 1 and x of I. So to find the average, you just add them together and divide by 2. Okay, so the midpoint rule, we get n areas of n rectangles. So the area of the first rectangle is f of x sub 1 bar times delta x. We add that to the area of the second rectangle, f of x sub 2 bar times delta x, and so on. And the nth rectangle, the height is f of x sub n bar times delta x. And then in sigma notation, from I equals 1 to n, the terms have the form f of x sub I bar times delta x. So this is the approximation of the definite integral using the midpoint rule. The midpoint rule is sort of tedious because you have to calculate, when you're applying it, you have to calculate the midpoints of all of those intervals. Okay, another way to approximate a definite integral is to use the trapezoidal rule. The trapezoidal rule is nice because it's just the average of the left-hand sum and the right-hand sum. So L sub n plus R sub n divided by 2. But it's called a trapezoidal rule because when you add, or when you take the average of a left-hand sum and a right-hand sum on an interval, it's exactly the same area you get by finding the area of a trapezoid. So this is a trapezoid. You might remember a trapezoid has 4 sides. One pair of sides is parallel, and the other 2 opposite sides are not parallel. So if you connect, this ordered pair is x sub 0, f of x sub 0. And this ordered pair is x sub 1, f of x sub 1. So connect those with a line segment, and you form a trapezoid. And the area of that trapezoid is the average of the left-hand sum and the right-hand sum for that interval. It's not too hard to show geometrically, but hey, and it turns out if you add the terms of the left-hand sum and the right-hand sum and then divide it all by 2, you'll end up with delta x over 2 times the quantity f of x sub 0 plus 2 times f of x of 1 plus 2 times f of x of 2, so on. At the other end, the second to the last term is 2 times f of x of n minus 1, and the last term is f of x of n. Let's see, my other page, what did I do with it? Oh, there it is. Well, the other page is kind of messy. So I'll just explain again. If you write out the terms for the left-hand sum and the right-hand sum and then add them together and then divide by 2, well, all of the middle terms occur twice. That's why the coefficients of f of x of 1 up through f of x of n minus 1 each has a coefficient of 2. And the farthest left endpoint only occurs once. F of x of 0 occurs once. And the same with the rightmost endpoint, f of x of n. And then you're taking the average, so delta x divided by 2. But this formula is not too hard to memorize. Okay, that brings us to the next method for approximating definite intervals. This one is called Simpsons Rule. So Simpsons Rule is more elaborate, but it's as far as approximating integrals, definite integrals, it's a superior method to the other three. Okay, so the underlying construction of Simpsons Rule is based on parabolas fitted through 3 points on the graph of the integrand over pairs of consecutive subintervals. The first parabola is fitted through 3 points on the graph of the integrand over the first 2 subintervals. The second parabola is fitted through 3 points on the graph of the integrand over the third and fourth subintervals, and so on. So we're just picking consecutive pairs of subintervals, fitting a parabola through 3 points on the graph of the function, and then finding the areas of those parabolas on the dual subintervals. But since we're taking pairs of subintervals, it makes sense that the value of n is even when you're applying Simpson's rule. Okay, so I'll just do a diagram on the first pair of subintervals. So from x sub 0 to x sub 1 and then to x sub 2. First, I'll try to draw, pretend like this is a part of a parabola. And then points on the parabola corresponding to x sub 0, x sub 1, and x sub 2. Are here, here, and here. So this blue line is the parabola. that is fit through those 3 points. But suppose the graph of f also passes through those 2 points, but it won't necessarily look like a parabola. It can do a lot of things. So this is just one possible graph of f of x, y equals f of x, is the red line. And then we fit a parabola through those points. So the ordered pair for this one is x sub 0, f of x sub 0. For this one, the ordered pair is x sub 1, f of x sub 1. And through that one, x sub 2, f of x sub 2. Okay, so the area that's below the parabola is what we're using to approximate that portion of the definite integral. Okay, so it turns out that if we were to just integrate f of x on the interval from x sub 0 to x sub 2, and that definite integral is approximately equal to the area under that part of the parabola. And it turns out that that's approximately equal to delta x divided by 3 times the quantity f of x sub 0 plus 4 times f of x sub 1 plus f of x sub 2. In the textbook, there's an explanation of how to do this. They use a more handy interval to show it, but it's only about a page and a half, and you can probably follow it if you read it. Okay, so this construction occurs on each pair of subintervals. So the full interval from, or the definite integral from a to b, will be approximately equal to n divided by 2 of those sums. That's why n has to be even. Okay, so the first one on the 2 subintervals from x sub 0 to x sub 2. So I'll rewrite this so we get delta x over 2. I'll try to write a little smaller so we can fit more in. Okay, then on the interval from x sub 2 to x sub 4, we get delta x over 3 times the quantity f of x sub 2 plus 4 times f of x sub 3 plus f of x sub 4, and so on and so on and so on. And the last pair of subintervals gives us this quantity, delta x over 3 times f of x of n minus 2 plus 4 times f of x of n minus 1 plus f of x of n. Okay, when we add all of those terms up, can you see what's going to happen? If we add all of them up, well, they all have a factor of delta x over 3 out front. So we can write delta x over 3. Let's just look at the first two terms up here. What's going to happen when we combine like terms here? Well, there's only one f of x sub 0 term, right? So we'll put f of x sub 0. There's only one f of x sub 1 term, and it has a coefficient of 4. So we'll write plus 4 times f of x sub 1. But then what? What comes after that? Yeah, we have f of x sub 2 plus f of x sub 2. So we get 2 times f of x sub 2. And then the next term is plus 4 times f of x sub 3. And what do you suppose will happen next? So this next term that I didn't write, but it's in the 3 dots, it's also going to have an f of x sub 4 term. So we're going to get 2 times f of x sub 4. And this pattern in the middle, sorry, this is supposed to be 2 times f of x sub 4. The middle terms follow this pattern, coefficient of 4 followed by coefficient 2, followed by 4, followed by 2, and so on. Okay, so at the other end, let's see, the third to the last term is plus 2 times f of x of n minus 2. The second to the last term is 4 times f of x of n minus 1. And the last term has a coefficient of 1, f of x of n. Okay, so down here I'll write this Simpsons rule a little bit more concisely. So we have delta x over 3 times f of x sub 0 times plus 4 times f of x sub 1 plus 2 times f of x sub 2, and so on. And then at the other end, we have 2 times f of x of n minus 2 plus 4 times f of x of n minus 1 plus f of x of n. Okay, if you practice memorizing this, it's not too hard. You'll want to make sure that you have this memorized by the time you take next Friday's test. So in 9 days. But it's not too hard. Just you'll get familiar with the pattern of the coefficients. Okay, I'll make a note of that. Memorize this and also the trapezoidal rule. Okay, let's move on to the next page. So on this one, suppose f of x is a continuous function such that f of x is greater than or equal to 0 on the domain interval from 0 to 12. Use the trapezoidal rule and Simpsons rule to approximate the definite integral of f of x from 0 to 12, which is the area between the graph of f and the x-axis on the interval from 0 to 12. Well, I'm a little bit redundant because a little bit. These function values are positive. But that in general wouldn't necessarily mean that f of 1 is positive. So the first statement helps us know that what we're trying to approximate is just the area below the graph of f. So first, let's use the trapezoidal rule. So how many subintervals are there? Six? Yeah, 6. We have 7 endpoints, but there are 6 subintervals. So for both the trapezoidal rule and the Simpsons rule, delta x is 2. That's the length of each subinterval. And since there are 6 subintervals, n is 6. So let's just write the general formula for the trapezoidal rule on n subintervals. So it's delta x over 2 times f of x of 0 plus 2 times f of x of 1, and so on. At the other end, 2 times f of x of n minus 1 plus f of x of n. So if n equals 6, the trapezoidal rule for n equals 6 is denoted t sub 6. Delta x is 2, so 2 divided by 2. Okay, so f of x of 0 corresponds to f of 0. F of 0 is 4. And then plus 2 times 8 plus 2 times 9 plus 2 times 10 plus 2 times 6 plus 2 times 5, and then plus 2. 2 divided by 2 is 1, and we can add these up pretty fast, pretty quickly. We get 4 plus 16 is 20, plus 18 is 38, plus 20 is 58, plus 12 is 70, plus 10 is 80, plus 2 is 82. So I get 82. Okay, so that's the approximation using the trapezoidal rule for the area below the graph of f on the interval from 0 to 12. Okay, now let's use Simpsons rule. So just for practice, let's write down the general formula for Simpsons rule. It's delta x over 3 times the quantity f of x of 0 plus 4 times f of x of 1 plus 2 times f of x of 2, and so on at the other end, 2 times f of x of n minus 2 plus 4 times f of x of n minus 1, and then plus f of x of n. Okay, so for n equals 6, s sub 6 denotes the Simpsons rule. Delta x is 2, so we have 2/3. And then f of x of 0 is 4. And then plus 4 times 8 plus 2 times 9 plus 4 times 10 plus 2 times 6 plus 4 times 5, and then plus 2. Okay, so 2/3 times this quantity. So 4 plus 32 is 36, plus 18 is 54, plus 40 is 94, plus 12, 106, 126, 128. So 2/3 of 128 is, it's about, well, it's exactly 85 1/3. So the two approximations are fairly close. Okay, and the next one, use the trapezoidal rule and Simpsons rule with n equals 4 to approximate the integral. Then find the exact value to compare. Okay, so the definite integral of 1 over x squared dx from 1 to 5. And if n equals 4, then delta x equals 1 in each of those cases. So we can construct a table of values. So f of x is 1 over x squared. So when x is 1, f of 1 is 1, f of 2 is 1/4, f of 3 is 1/9, f of 4 is 1/16, and f of 5 is 1/25. T sub 4, the trapezoidal rule for n equals 4. Delta x is 1. So in the trapezoidal rule, it's delta x divided by 2. And then the first output is 1, and then plus 2 times 1/4 plus 2 times 1/9 plus 2 times 1/16, and then plus 1/25. I'll leave the rest of that for you to do. That's pretty simple arithmetic. Let's write down the Simpsons rule for S sub 4. So Simpsons rule, delta x over 3. So delta x is still 1, so 1 divided by 3. And then the first output plus 4 times the second output plus 2 times the third output plus 4 times the second to the last output, and then just plus the last output. So this is the Simpsons rule for n equals 4. So go ahead and compute those numbers and you can compare them. Okay, so let's look at error estimates. The error estimate for the trapezoidal rule. This says if the second derivative of f is continuous on the domain interval from a to b, and if the absolute value of the second derivative of f of x is less than or equal to some number k, assuming that that's restricted to the interval from a to b, then the error, capital E sub t, between the exact value of the definite integral and t sub n is given by this inequality. The absolute value of the error is less than or equal to k times b minus a to the third divided by 12n to the second, where n is the number of subintervals. The error estimate for the midpoint rule, this one is pretty close to the same as the error estimate of the trapezoidal rule, but it is a little bit different. On this one, we still have the second derivative being continuous on the domain interval from a to b, and the absolute value of the second derivative is less than or equal to k on that interval from a to b. Then the error E sub m between the exact value of the definite integral and m sub n is this inequality. The absolute value of the error for the midpoint rule is less than or equal to k times b minus a to the third divided by 24n to the second. Okay, so the only difference between the error estimate for the trapezoidal rule and the midpoint rule, in the trapezoidal rule we have this constant 12 multiplied by n squared in the denominator, and the midpoint rule has 24 instead. Okay, the error estimate for Simpsons rule. Well, this one requires a little bit more work. This is the notation for the fourth derivative of the function f. If the fourth derivative of f is continuous on the domain interval from a to b, and the absolute value of the fourth derivative on that interval is less than or equal to some constant k, then the error E sub s between the exact value of the definite integral and s sub n is the absolute value of the error is less than or equal to k times b minus a to the fifth divided by 180 times n to the fourth, where n is the number of subintervals. Well, we're about out of time. On Friday, we'll finish up Chapter 7, Section 7, and after that, we'll get started on Chapter 7, Section 8. But that's all for today. So go ahead and sign in for attendance.
I will be missing class on Fridays because we have another track.
This Friday?
Yep.